G'day, welcome to this video on uniform continuity. Uniform continuity is a special type of continuity that is very similar to the standard definition, but differing slightly in the placement of the existence of a delta and the relationship between x and a based on that delta. And the key difference is that a is now independent of our delta. Or maybe what I should say is that delta is actually independent of our a value. Before, we would look at all epsilon greater than 0 and a specific point A in our domain, and then check if the epsilon delta definition worked for that point. But now we need to apply our epsilon delta definition in a universal way that works for all points in the domain A. So the idea is that the way that x is continuous is uniform. It's the same way across all points in its domain. And it's a very subtle difference in the definition, but mathematically makes a difference because in our proof, when we're proving this is true, we cannot choose our delta in response to the A. We have to choose our delta independently and then show that it works for any A in the domain. So one quick comment is that uniform continuity implies continuity, but of course, continuity does not imply uniform continuity, as uniform continuity is the stronger type of continuity. Okay, so just some intuitive examples here to explain uniform continuity graphically. Here, if you're looking at being within delta of your input here, so we've got this center here, and then 2 delta is the width here, because you can be plus delta or minus delta from that center. The idea is that the way that your function behaves is that you will be within 2 epsilon. You'll create a 2 epsilon box, so plus or minus epsilon here, centered at this f of a value, where you can go epsilon above or epsilon below, and always be within epsilon distance of that f of a value, in such a way that that is going to be the same relationship between your input and your output, regardless of where you are in your domain. So if we were to change to looking at over here, the idea is that if you're within delta, and that's the exact same delta of your input here, you'll have the same boundary plus or minus epsilon of that center at this different domain input. And then same goes here. If you were to look at a input here, you will have the same plus or minus epsilon distance between f of a minus delta and f of a plus delta. And the idea here is that you have this convergence and continuity occurring in a smooth way that is consistent across the domain. It's being continuous in a uniform way. Okay, so let's look at an example of how we can prove a function is uniformly continuous. So the one that we'll look at is this example here, where we want to prove that this function is uniformly continuous. Let's do the scratch work together to essentially solve the question, and then I'll walk you through the proof solution of formalizing that argument. Okay, so the question that we want to do is prove, I'm going to use this pencil, prove f that maps the real numbers to the real numbers and x to 1 on 1 plus x squared is uniformly continuous. That's our question. So our scratch work is that we want to show all epsilon greater than 0, there exists a delta greater than 0, such that every x and a in the domain where x minus a is less than delta, we have f of x minus f of a is less than epsilon. So that's our definition of uniform continuity. And the purpose of our scratch work is if we flash forwards to our proof, we want to show for any arbitrary epsilon greater than 0, given this delta we choose, this holds. Our goal of the scratch work is to find how to choose this delta in response to that epsilon so that we can have the rest of this definition hold. So we need to focus our attention on this and basically assume that this whole definition is holding, and then work backwards to find out the information, work backwards to find out the delta that we need to ensure that this is holding. So consider f of x minus f of a, which is equal to just plugging that into this function definition here, 1 on 1 plus x squared minus 1 on 1 plus a squared. And because we know that we have this relationship, our goal is to try and simplify this down into some expression that contains the absolute value of x minus a. So let's progress by joining this together. So if we give them the same denominator, then we can just take the difference of the numerators. So let's multiply this by 1 plus a squared and this by 1 plus x squared, and then we'll have the same denominator. And taking the difference, we'll have 1 plus a squared minus 1 plus x squared divided by 1 plus x squared multiplied by 1 plus a squared, like this. And then the ones are going to cancel out. We have a squared minus x squared divided by 1 plus x squared multiplied by 1 plus a squared. And we have the difference of perfect squares on the numerator there. So we have a plus x multiplied by a minus x. And then we need to include obviously the denominator, and because we are targeting this one here, let's put the denominator on this one. Okay, and this here is the same as this. It doesn't matter the order of which you do the subtraction, the absolute value will be the same. And we can use the triangle inequality to separate this here. So I'm going to rearrange it like this. X minus a. So this is less than or equal to x minus a multiplied by So I'm using the triangle inequality here to separate the a plus x on the numerator to different terms. And of course the denominator has to carry through there. And let's think about what this is here. 1 plus x squared multiplied by 1 plus a squared. Well, the square of something will always be positive or 0. And then 1 plus that means that you'll have it multiplied by 1 or higher. And that will always increase the denominator, which is already a positive number. So we can essentially get rid of this and this as a part of that expression, because this will be less than or equal to deleting those components of the denominator. Essentially, they're just increasing the denominator, which is making the whole thing smaller. So when we remove them, we know that this overall expression is less than or equal to the removal of those. So just to write that in, we have that. And then the absolute value of a divided by 1 plus a squared, that is always going to be less than or equal to 1, regardless of what a is. You can do a separate proof of that if you don't believe me, but this is always going to be less than or equal to 1, and this is going to be less than or equal to 1, regardless of what a and x are. So that's less than or equal to 1 plus 1. And then this is strictly less than delta. So that's strictly less than 2 delta. And we want that to equal epsilon. So now we know how we should choose delta in response to epsilon, where we choose delta to equal epsilon on 2. If delta is epsilon on 2, that'll give us what we want. And I'll leave this as an exercise to prove. Okay, and then now we need to formalize this proof. So I'll flick to my neat notes. Okay, essentially the purpose of the scratch work is to determine how to choose your delta in response to epsilon. And once you have that, you then need to convert it into your formal proof. So let epsilon be greater than 0. I think it's more clear to do it this way. Let epsilon be greater than 0. From our scratch work, we now know to choose delta to equal epsilon on 2. And we can trust that this is a positive number as epsilon is also positive. Then we want to let a and x be real numbers such that x minus a is less than delta. And now we want to consider the absolute value of f of x minus f of a. This is satisfying the premise of our uniform continuity definition, and we want to prove that the premise implies the conclusion here that f of x minus f of a is within epsilon of each other. So we can expand out what f of x and f of a is, which is that. We can do the same steps as our scratch work to get down to this. Then we can do the difference of perfect squares to give us this. I'm not sure. I think that it might be a photocopy error, but just have a look at what that is. Just the denominator there is gone from the photocopying. So we're moving that to the side, and then we've got a plus x here with the whole denominator being there. That is less than delta, and we know delta is equal to this, so we can go from here to here. And then we use our triangle inequality. Just put that there. And then we have this. And like I said before, that is less than or equal to 1, which gives us this. And then the whole chain of logic there gives us overall, if I scroll back up here, that this is strictly less than epsilon. So therefore, for all epsilon greater than 0, there exists a delta greater than 0 where any x and a that's a real number, where x minus a is less than delta, implies that f of x minus f of a is less than epsilon. And that is our definition for f to be uniformly continuous or not. All right, in summary, this is how you prove something is uniformly continuous, which is a little bit more difficult than proving just standard continuity, as you have less control over your delta. You cannot pick delta in response to a. Uniform continuity as a property is useful in several theorems in real analysis. You don't see many of those theorems in microeconomic theory, but hopefully understanding the broader proof concept here will help extend your own ability to do proofs and to understand what continuity is more rigorously. I hope you found this video helpful. Thanks.